Good evening. Tonight, we're diving into a part of our planet that most people will never see: the deep ocean, a world of total darkness, crushing pressure, and temperatures near freezing, but also a world surprisingly alive. Far below the waves, on the abyssal plain, scientists have discovered oxygen being produced without a single ray of sunlight. That's right, oxygen, the same gas we breathe, forming in pitch darkness through chemical reactions we are only now beginning to understand. Even stranger, around hydrothermal vents, underwater hot springs where water reaches hundreds of degrees Celsius, life thrives in ways that were once thought impossible. Microbes convert chemicals like sulfur and iron into energy in a process called chemosynthesis, forming the base of ecosystems that support tube worms, clams, and even species never seen anywhere else on Earth. And beneath it all, the ocean floor itself is being shaped by volcanoes erupting under kilometers of water. These submarine eruptions release heat, chemicals, and minerals that feed the chemical reactions and life forms above them. The result is a hidden network of energy and chemistry, a living, interconnected system operating far out of sight, yet essential to the health and balance of our oceans. Tonight, we'll follow the trail from oxygen to life to molten rock and see how these processes link together to create a deep sea world that is alive, dynamic, and more complex than anyone imagined. Let's begin with a discovery that quietly challenged one of the most basic assumptions in ocean science. For more than a century, scientists believed that oxygen in the ocean could only come from one source: photosynthesis. In simple terms, sunlight strikes plants or algae, they use that energy to split water molecules, and oxygen is released as a byproduct. If there was no sunlight, it meant no oxygen. That rule was considered fundamental. But the deep ocean does not follow that rule. Thousands of meters below the surface lies the abyssal plain. This is a vast, cold, nearly flat region of the ocean floor that covers much of the planet. It exists in complete darkness. It is far too deep for sunlight to ever reach it. Temperatures hover just above freezing. For a long time, scientists assumed this environment was dead and empty, nothing but sand, dirt, and rocks. That assumption is now being re-examined. During recent deep-sea expeditions, researchers detected something unexpected: oxygen being produced directly on the seafloor in total darkness. This oxygen was not drifting down from surface waters, it was being generated locally. The source appears to be metal-rich mineral nodules scattered across the abyssal plain. These nodules are rounded, rock-like formations made primarily of manganese along with nickel, cobalt, and iron. They form extremely slowly, building up layer by layer over millions of years. What makes these nodules remarkable is not just their composition, but how they behave chemically. Under certain conditions, the metals within these nodules can create tiny electrical differences between their surfaces and the surrounding seawater. In practical terms, this means electrons can slowly move from one location to another. The effect is very small, but measurable, and those moving electrons matter. In seawater, oxygen is bound up inside molecules such as water. When electrical energy is present, even at very low levels, it can drive chemical reactions that split those molecules apart. One of the results of this process is free oxygen released directly into the surrounding water. This reaction does not rely on sunlight. It does not require plants or algae, and it does not require life at all. Because it occurs in complete darkness, researchers have begun referring to it as dark oxygen. To be clear, this is not producing oxygen on the scale of surface photosynthesis. The amounts measured are small, but in the deep ocean, even small changes in oxygen concentration can significantly affect local chemistry and biological activity. And because this discovery is so recent, there is still much scientists do not fully understand. Researchers are now working to determine how stable these electrical potentials are, how widely this process occurs across the seafloor, and how much oxygen it can realistically contribute over long periods of time. It's also not yet clear how dark oxygen interacts with other chemical systems already operating in the deep ocean. What scientists do suspect is that this is not a single, isolated reaction, but part of a broader network of slow, low-energy processes that shape deep-sea chemistry over geological timescales? Answering those questions will require more seafloor measurements, longer sensor deployments, and carefully controlled laboratory experiments. What is already clear is this: oxygen production in total darkness is possible, measurable, and occurring in places once assumed to be chemically inactive. And that realization leads directly to the next question. If oxygen and usable energy exist on the deep ocean floor, what uses it? The answer is reshaping how scientists understand life on Earth. In 1977, researchers exploring the seafloor near the Galapagos Rift discovered something no one expected: dense communities of living organisms clustered around cracks in the ocean floor. These cracks were releasing superheated water rich in dissolved chemicals. They became known as hydrothermal vents. At first glance, the environment seemed hostile to life. The water emerging from these vents can exceed 350 degrees Celsius. Pressure is extreme, and there is no sunlight at all. Yet life not only exists there, it flourishes. The foundation of these ecosystems is a process called chemosynthesis. Unlike photosynthesis, which uses sunlight to produce energy, chemosynthesis uses chemical reactions. Certain microbes are able to take chemicals like hydrogen sulfide, methane, or iron compounds and convert them into usable energy. In simple terms, these organisms treat chemicals the way plants treat sunlight. These microbes form the base of the food web. Larger organisms, such as giant tube worms, clams, shrimp, and crabs, either feed on them or live in direct partnership with them. Some tube worms, for example, have no mouth or digestive system at all. Instead, they house chemosynthetic bacteria inside their bodies, relying entirely on those microbes for nutrition. This discovery overturned a long-standing belief that all complex life ultimately depends on sunlight. Instead, it showed that energy from within the Earth itself can support entire ecosystems. What's especially relevant here is how closely chemistry and life are intertwined in these environments. Hydrothermal vents release not only heat, but a steady flow of minerals and gases. When these substances mix with cold seawater, they create chemical gradients, areas where concentrations of chemicals change sharply over short distances. Those gradients are what chemosynthetic microbes exploit. Oxygen, even in small amounts, can alter these chemical gradients. This is where discoveries like dark oxygen become important. While vents themselves often release fluids low in oxygen, the surrounding seafloor chemistry can vary dramatically depending on local conditions. Scientists are now studying how oxygen produced on the abyssal plain may interact with vent systems nearby, potentially influencing microbial activity and the structure of these ecosystems. The deep ocean, it turns out, is not a collection of isolated environments. It's a patchwork of chemical zones, shaped by geology, chemistry, and energy flow. And those zones are dynamic and teeming with life. New species are still being discovered around hydrothermal vents. Some survive temperatures and chemical conditions once thought incompatible with life. Others show metabolic pathways unlike anything seen at the surface. These findings don't just matter for ocean science. They inform our understanding of how life might exist on other worlds, places without sunlight, but with chemical energy beneath the surface. Which brings us to the final piece of this system. What powers these vents, drives these chemical reactions, and reshapes the ocean floor itself? To answer that, we have to go deeper into the volcanic forces operating beneath the seafloor. Far beneath the ocean floor, Earth's crust is constantly moving. Large plates of rock slowly pull apart, collide, and slide past one another. Where those plates separate, molten rock from deeper inside the planet rises toward the surface. This is where deep-sea volcanoes are born. Unlike the volcanoes we're familiar with on land, most of Earth's volcanic activity happens underwater. Along mid-ocean ridges and back arc basins, magma pushes upward through cracks in the crust, releasing enormous amounts of heat and chemically rich material into the surrounding seawater. When magma heats seawater trapped in the crust, that water becomes superheated and dissolves minerals from the surrounding rock. It then rises back out through the seafloor, forming hydrothermal vents. These vents are not static features. They appear, change, and sometimes disappear entirely as volcanic activity shifts beneath them. Recent advances in ocean monitoring have allowed scientists to observe these processes in real time. Seafloor sensors can detect earthquakes caused by magma movement, changes in water temperature and chemistry, signal when new vents are forming. In some cases, satellite measurements can even detect subtle changes at the ocean's surface caused by eruptions kilometers below. One well-studied example is axial seamount, an underwater volcano in the Pacific Ocean that has erupted multiple times in recent years. These eruptions were detected by seafloor sensors that recorded earthquakes, rising temperatures, and changes in seawater chemistry as magma moved beneath the crust. When the volcano erupted, fresh lava flowed across the seafloor, resetting local ecosystems and releasing heat and minerals into the surrounding water. Another is volcanic activity in the Mariana Back-Arc region, where eruptions have been documented producing massive chemical plumes and reshaping the seafloor. In this region, magma rises behind a subduction zone, creating intense heat that drives powerful hydrothermal systems. These eruptions release clouds of mineral-rich fluids into the surrounding water, spreading iron, sulfur, and other elements across large areas of the deep ocean. These eruptions matter because they supply the deep ocean with energy and raw materials. Volcanic activity releases heat that drives circulation of seawater through the crust. It delivers minerals like iron, sulfur, and manganese into the ocean, and it creates the chemical gradients that chemosynthetic life depends on. In other words, volcanoes don't just reshape the seafloor, they actively power deep sea ecosystems. This also helps explain why regions of the deep ocean can be chemically complex rather than uniform. Volcanic activity varies from place to place. Some areas are geologically quiet, others are constantly being recharged with heat and minerals. Over time, this creates a mosaic of environments across the ocean floor. Some regions favor oxygen-producing reactions, others support dense vent communities. Some do both. What's especially important is that these processes operate continuously over thousands to millions of years. Even slow, low-level volcanic activity can have a lasting impact on ocean chemistry and biology. The deep ocean is not being shaped by a single force. It is the product of constant interaction between geology, chemistry, and life. And when we step back and look at all of these elements together, a larger picture begins to emerge. When we look at everything together, oxygen forming in the dark, life thriving without sunlight, and volcanic energy shaping the seafloor, a remarkable picture emerges. The deep ocean is not a quiet, inert place. It's a dynamic, interconnected system where chemistry, geology, and biology work together in ways we are only beginning to understand. Consider this: metal-rich nodules produce tiny electrical potentials that create oxygen. That oxygen, even in small amounts, influences the chemical environment around it. Near hydrothermal vents, chemosynthetic microbes exploit chemical gradients created by the interaction of vent fluids and surrounding seawater. These microbes form the base of complex ecosystems, supporting tube worms, clams, shrimp, and even predators that have adapted to this lightless world. Beneath it all, volcanic activity continually reshapes the landscape. Eruptions inject heat, chemicals, and minerals into the system, driving circulation and sustaining the very reactions that produce energy and oxygen. Each vent, each nodule field, each eruption contributes to a living network that spans kilometers of the ocean floor. In other words, the deep ocean is a self-sustaining, chemically and biologically active circulatory system. Energy flows from the Earth's interior, chemistry distributes it, and life adapts to harness it. It's a hidden web of interaction, invisible to most, yet fundamental to the ocean's balance. This system also shows us how resilient life can be. Organisms have adapted to extreme pressures, total darkness, and fluctuating chemical conditions. They thrive not by sunlight, but by tapping into energy sources long overlooked. The very existence of dark oxygen and chemosynthetic ecosystems expands our understanding of where life can exist, not just on Earth, but potentially on other planets or moons with similar conditions. What's more, this perspective changes how we view the deep ocean's role in the global environment. Even though these processes happen far from the surface, They influence chemical cycles, support biodiversity, and contribute to the overall health of our oceans. The interplay of oxygen, minerals, heat, and life creates pockets of productivity in what was once thought to be barren space. Yet, despite all we've discovered, much remains unknown. We are still mapping nodule fields, tracking vent activity, and measuring chemical fluxes. We are still discovering new species with unique adaptations. Each expedition reveals more complexity, and each new measurement reminds us how little we truly understand about this hidden world. The deep ocean is a living system, powered by unseen forces, shaped by chemistry, energized by geology, and inhabited by life that defies imagination. It is a world that challenges assumptions, rewards careful observation, and continues to teach us that even in the darkest depths, the planet is alive with movement, energy, and possibility. This has been For What It's Worth. If you want more interesting information, please like and subscribe.